Okay, so we can start. Welcome to today's class. I hope I'm clearly audible and the slides are also visible. Just give me a minute. So we can start. In the last lecture, we studied the stability of the closed loop process. So one way to comment on the stability of the process was to analyze the transfer function. If the transfer function is given by g of s upon g of s is equal to numerator upon denominator, then this for any kind of closed loop transfer function, this denominator is known as characteristic equation, and the roots of these characteristic equations of the denominator are known as poles. And if the poles of the system lies in the left side of this axis, then we can say that the system is stable. That is, existence of positive pole leads to instability of the process. Let's say the poles of the system lies on this side, then the system is unstable. So we have to write the transfer function, then find the roots of the denominator, and then we can say about the stability of the system. Now the other approach in which we don't need to find the roots of the denominator, that is this Routh-Hurwitz criterion for stability. So uh, in this criteria, we have to write this characteristic equation in terms of the polynomial in terms of S, and then if this a naught should be positive. So if a naught is negative, then we have to change it to positive by multiplying by -1. And then all of these coefficients a naught, a1, a2, a3, all of this that should be positive, then only we can say that the system is stable. The other thing is we have to calculate each of these coefficients of this first column, A0, A1, A1, B1, C1. And if they are positive, then we can say that the system is stable. And if any one of them is also negative, then we can say that the system is unstable for that pole. Then we studied about this frequency response analysis, in which given the transfer function, let's say for the first order system, if it is Kp is equal to tau s plus 1, and if I want to analyze its response, that's how it will proceed with time, then I can simply do this frequency response analysis, that is replace the s by j omega, that is now it will become j of j omega is equal to Kp upon tau j omega plus 1. Then we can write this in terms of its real and imaginary part, that is a plus ib. Then on the basis of this, we can calculate the amplitude ratio. So for this system, it is Kp upon under root of omega square tau square plus 1. And we can also calculate the phase lag or the phase angle, that is tan inverse minus of b by a. So based on this amplitude ratio, we can say that if this is my input, sinusoidal input, and if amplitude ratio is 1, that means the output will be also lying within this range. So the maximum and the minimum value of the output will lie within this range given by the input. That is what we mean by amplitude ratio equal to 1. If amplitude ratio is greater than 1, that means our output will cross this limit. It will go beyond this limit. And so this is we studied. Then the other thing to analyze the response of any transfer function is via this Bode diagrams. So in this Bode diagram, we plot the graph between, let's say, either frequency, or we can also plot between omega tau. And on the y-axis, we can have the amplitude upon k, constant k. And on the bottom graph, we have this omega and omega tau versus this phase lag. So if omega tends to 0, that is on this side, we define this as low frequency asymptote. And if it's omega, that is frequency tends to infinity, then we call this as high frequency asymptote. And the frequency at which omega is equal to 1, we call it as corner frequency. So this is for first order system. Similarly, we can draw the Bode plot for second order system and also closed loop systems. And then we looked upon few of the questions related to this feedback control, feed forward control from the previous lectures. Then we looked upon couple of questions related to Routh array. So these were the questions. So we will start with the same topic today. We'll solve the few questions related to Routh array, and then we will move on to the other topic related to this phase margin, gain margin, and Bode stability criterion. If you have any doubt meanwhile during the lecture, you can unmute yourself and speak. So today we will be covering this Bode stability criteria and the definitions of gain margin and phase margin, and solve the numericals related to that question. But before that, first let us solve a couple of questions related to this Routh array. So the first question that we are solving today is from GATE 2017, question number 52. So here we have been given the characteristic equation of a closed loop system. So this is our characteristic equation, and we have been provided k is greater than 0. Then the value of k beyond which the system just becomes unstable, rounded off to nearest integer is dash. So we have to find the value of k for which the system becomes unstable. So for this, simply we can write the Routh array for this, and then check the values of the first column. such that it is always positive, and based on that we can comment on the stability of the system by analyzing the value of k. So let's take a look on the video solution. We are solving question 52 of GATE 2017 chemical engineering paper, and the question is unstable. To find the value, for that we will be using Root's criteria for stability, which states that given the root error of this form, if the value of all these values in the first column are greater than 0, that is positive, then the system will be stable. And this A0, A1 are the coefficients of the nth order polynomial in terms of A. So over here in this question, the characteristic equation we have been given is 6s cube plus 11s square plus 6s plus 1 plus k is equal to 0. So in this root theory, the value of A0 will be 6. So this is A0, A1. A1 will be 11, A2 will be 6, and A3 will be 1 plus k. And then we need to find the values of A1, A2, B1, and all the other values will be 0. So this will be 0, 0. This will also be 0. So let's just find the value of A1. The value of A1 is A1 into A2 minus A0, A3 upon A1. That is, we can write it as 11 into 6 minus 6 into 1 plus k upon A1, that is 11. It will become 66 minus 6 minus of 6k upon 11. It is A1 is equal to 60 minus 6k upon 11. The value of A2 is A1 A4 minus A0 A5 upon A1. So over here this A5 is 0. So this entire term will become 0 and A1 will get cancelled out. That is A2 will be equal to A4. And that is also 0. That is A2 will be 0. And now B1. The value of B1 is A1 A3 minus A1, and A2 is 0 upon A1. That is, this will also get cancelled, and the value of B, we will be getting it as A3, and A3 is 1 plus K. That is, B1 is, we are getting 1 plus K. Now this 6 is greater than 0, 11 is greater than 0. And for stability, A1 should be greater than 0, and also B1 should be greater than 0. Now in the given question, we have been given that K is greater than 0. That implies 1 plus K will also be greater than 0. That is, this is also satisfied. Now we need to comment on this A1. So A1 should be greater than 0. That implies 60 minus 6K upon 11 should be greater than 0. It is 60 minus 6K should be greater than 0. That is 6K should be less than 60. That will give us K should be less than 10 for stability. So the final answer, we can write that the value of K beyond which the system just becomes unstable, rounded to nearest integer, will be 10. So if you have any doubt in this question, you can ask, or we can move on to the next question. So the next two questions are very similar, so we will just solve one of them. So this is question number 2. This is question number 52 from GATE 2016, and the question is: a PI controller with time constant of 0.1 minute is to be designed to control a process with transfer function GP is equal to 10 upon s square plus 2s plus 100. Assume the transfer functions of measuring element, final control element are both unity. The gain of the controller that will constitute the critical condition for the stability of PI feedback control system is dash. So in this question, we have to find this controller gain. So here we have been given this process transfer function GP, then the transfer function for this measuring element is 1, transfer function for final control element GF is also 1, and the controller that we are using is PI controller. So for this PI controller, the transfer function is given as GC is equal to K 1 plus 1 upon tau I S. So this K is the controller gain and tau is the integral time. So over in this question, we have been given the integral time constant as 0.1 minute and have been asked to find this constant K. So again, for this question, we have to draw this feedback control system. That is the block diagram of feedback control system. Then write the transfer function of the entire closed loop transfer function of the entire block diagram. And then we can use the root array to find the criteria for the stability, and based on that we can find this value of the controller gain. So let's take a look on the video solution. This closed loop feedback control system. So the set point of the system will be YSP. Then we have been provided a PI controller. So we can write the transfer function of the PI controller as GC is equal to K 1 plus 1 upon tau I into S, and tau I we have been given as 0.1 minute. Then we will be having a final control element GF, the process transfer function as GC is equal to 10 upon S square plus 2S plus 100, and then we'll be taking the output Y. Again, we'll be measuring it using the measuring element G1 and passing it to the system over here. So the characteristic equation for this system, we can write it as 1 plus multiplication of all these blocks in the open loop, that is 1 plus open loop transfer function is equal to 0. So that will be 1 plus K 1 upon tau is into GF. GF we have been given as 1. GC is 10 upon S square plus 2S plus 100 into GM is 1 is equal to 0. Basically, we got this from this 1 plus GL is equal to 0, and G open loop was GC, GF, GM, and GP is equal to 0. Then we replace the values of this transfer function to get this equation. Now we need to simplify this equation, and then we will be having the equation in that will be a polynomial in terms of S, and then we can use the roots criteria for stability to solve to comment on the stability of the system by comparing the coefficients. So let's just put the value of tau I as 0.1 into over here and simplify this further. So we will be having 1 plus k. So tau I is 0.1, so it will go over here and it will become 0.1 s plus 1 upon 0.1 s upon 10 s square 2s plus 100 is equal to 0. We can simplify this further to write 1 plus kc into s plus 10 upon 0.1 s cube plus 0.2 s square plus 10s is equal to 0. So this will become 0.1 s cube plus 0.2 s square plus 10s plus s times kc plus 10 kc upon denominator s cube plus 0.2 s square plus 10s is equal to 0. That is, the polynomial that we are having is 0.1 s cube plus 0.2 s square plus 10 plus kc into s plus 10 kc is equal to 0. This is the polynomial we will be getting, and using the root array the system will be stable if the values of all these coefficients in the first column is greater than 0. So over here a0 we are having it as 0.1, a1 we are having it as 0.2, a2 is 10 plus kc and a3 is 10 kc. The rest, this a4 a5 will be 0. And now we can find the values of a1. So a1 is a1 a2 minus a0 a3 upon a1. So let's just find its value. Ten plus kc upon 0.2. That is 2 plus 0.2 kc minus, over here we are having 10 kc, so this will become minus kc upon 0.2. So this value should be greater than 0. That is 2 plus 0.2 kc minus kc should be greater than 0. That is 2 minus 0.8 kc should be greater than 0. So from here we will be having the value of kc as less than 2 upon 0.8. The value of kc should be less than 2.5. So we have this value of a1. Now we need to find the value of a2 so that we can find the value of b1. So a2 will be this, a5 is 0. So this term will become 0 and a1 will get cancelled out and we will be having a4. So a4 is also 0, that is a2 will be 0. So correspondingly this term will become 0 and over here we will be getting b1 is equal to a3. Rest of term will be 0. So a3 is 10 kc, so that will be also greater than 0. That is the only criteria that we are having, is the value of kc should be less than 2.5. So we looked on this question in which we had to first draw the block diagram of the closed loop system and then use the Routh array to find the value of the controller gain. So the next question, we can just look. So in this question, we have been given a process with a transfer function Gp is equal to 2 upon s minus 1 is to be controlled by a feedback proportional controller with a gain of Kc. If the transfer function of all the other elements in the closed loop are unity, which one of the following produces the stable closed loop system? So this question is very similar to the previous question, but in the previous question, we were given this PI controller for which the transfer function was Kc is equal to 1 upon 1 plus tau is, but in this question we have been given the proportional controller, and for that the transfer function will be simply Kc. That is the only difference between these two questions. So yes, so we won't be solving this question. So just to give a look on the solution, we will draw this block diagram, right? The transfer function, the denominator will be characteristic equation, and then we will be having this characteristic equation. So in this question, we are simply having this first order system. So I don't think we need to find this Routh array. We can simply find the value of Kc by using the property that the poles of the system should be less than 0, then only the closed loop system will be stable. So over here we are using this on the basis of that we will be getting this range of Kc beyond which the system will be stable. So now we will be looking on this Bode stability criteria, and related to that Bode stability criteria, we'll be covering this gain margin and phase margin. So according to this Bode stability criteria, we define each of these terms. So the stability criteria is given by this statement, which states that a feedback control system is unstable if the amplitude ratio corresponding to the open loop transfer function is greater than 1 at the phase crossover frequency. The first thing to notice that we will be analyzing the open loop transfer function. Okay. So given any system, we'll be first writing the open loop transfer function, and then it states that the system is unstable if the amplitude ratio is greater than 1. That is, we will be finding the amplitude ratio of this open loop transfer function, and if it is greater than 1, that implies the system is unstable. And this amplitude ratio that we are calculating should be calculated at this phase crossover frequency. So this phase crossover frequency is an important term, and we will see that how can we calculate this phase crossover frequency. So this phase crossover frequency, we can write it by omega pc, and it is the frequency at which the phase shift is equal to minus 180 degree. Okay, so the phase shift is defined as the phase angle. So given a transfer function of the form of, let's say, a plus ib, then the phase shift, we call it as tan inverse minus b by a. And if there are multiple systems in series or in parallel, then for that system, we can write the transfer function, then find the phase shift. So the frequency at which the phase shift is equal to minus 180 degree, then that frequency we call it as this phase crossover frequency. Similarly, we define this gain crossover frequency omega gc, and it is the frequency at which the amplitude ratio is 1. So if the frequency omega at which amplitude ratio equal to 1 is known as gain crossover frequency, and the omega at which the phase shift, that is we define it by phi, is equal to minus 180 degree or minus pi, then we call that as phase crossover frequency, that is phi of pc. So yes, the stability criteria states that if at the phase crossover frequency, the amplitude ratio should be less than 1 for the stable system, That is what this Bode stability criteria states. So if we take a look on the example of this Bode plot, so first of all, we have to find the phase crossover frequency. That is the frequency at which the phase shift is minus 180 degree. So the first plot gives us the plot of amplitude ratio versus frequency. The second plot gives the second Bode plot gives us the relation between the phase shift or phi versus omega. So over here we can see that if the phase shift is minus 180 degree, then the corresponding this frequency, we call it as phase crossover frequency. And according to Bode stability criterion, we have to find this amplitude ratio at this omega pc, and that should be less than 1. So we have to go above on this amplitude ratio plot, and if this amplitude ratio, that is this value, if it is less than 1, that implies the system is stable. So yes, we have to remember these two terms. First is the phase crossover frequency. So to find the phase crossover frequency, we have to find the phase shift of the system and then equate it to minus pi to find the value of omega, and that omega is our phase crossover frequency. And after calculating this omega, we have to calculate the amplitude ratio by using this omega, and if it is less than 1, that implies that our system is stable. So that is what Bode stability criterion is. And on the basis of this Bode stability criteria, we can define these two terms, gain margin and phase margin. So basically they can be called as this safety factor. So that are incorporated so that our system can handle the uncertainties in modeling or uncertainty in measurements or the noise. That is why we define this gain margin and phase margin. So gain margin, we define it at let x equal to this. So basically this is our amplitude ratio. So if x is our amplitude ratio, then the gain margin is given by 1 upon x. That is, we can straight away write that gain margin is 1 upon amplitude ratio at this phase crossover frequency. That is an important thing at omega pc. Then similarly, we define this phase margin as if theta is our phase shift or phase lag, then we define this phase margin, let's just call this pm, as 180 degree plus theta. And this theta we need to calculate at gain crossover frequency, and the gain crossover frequency is the frequency at which the amplitude ratio is 1. So just something to remember, if we have to calculate this phase margin, then the amplitude ratio should be 1, and if we have to calculate this gain margin, then the phase, then we have to calculate that is phase crossover frequency, that is phase lag should be minus 180 degree. And yes, if both the gain margin and phase margin are positive, then the control system is stable. This means that we are having sufficient margin such that our system will lie within the bounded output range. That is, the system is stable. And if both the gain margin and phase margin are equal to 0, then the control system is marginally stable. And if the gain margin and or phase margin R is negative, then the control system is unstable. So in the earlier slide, we defined this gain margin as 1 upon amplitude ratio and phase margin as 180 plus theta. So we have to remember these two terms. And then we define this ultimate gain from this Bode stability criterion. So the Bode stability criterion states that the maximum value of controller gain that can be chosen for a stable closed loop response is called as ultimate gain or KU. That is, let's say for any controller that we are using, if the controller gain is Kc, then it should not exceed this ultimate gain of Ku. So we define this ultimate gain such that it is always larger than this controller gain Kc. That is, yes, in other words, the value of controller gain must be less than Ku to ensure the stability. So the gain margin is a design parameter such that this Kc is equal to Ku upon Gm. So this is a design parameter, so it won't come from the system. We will be providing the gain margin of the system, and on the basis of the gain margin, we will be calculating this ultimate gain. So yes, these three equations we need to remember. The first one is gain margin is the inverse of amplitude ratio. The phase margin is 180 plus 5, and the ultimate gain, we can just write it as Ku is equal to Kc into gain margin. And if we are calculating this gain margin, then we have to remember that the amplitude ratio should be calculated at the phase crossover frequency. And if we are calculating this phase margin, then this phase shift should be calculated at this gain crossover frequency, that is amplitude ratio equal to 1. So yes, ultimately both of these factors, this phase margin is also another safety factor to control the design. So it is the extra phase lag needed to destabilize the system. So I hope this gain margin and phase margin are clear. We will solve a few questions related to that and it will be more clear. If you have any doubt, you can write it in the chat box. So the first question that we are looking related to is gain margin and the phase margin is from GATE 2020, question number 53. So the question is, consider the closed loop system where GC, GF, GP are the transfer function of the controller, final control element, and the process respectively. Y and YSP are the response and set point respectively. For the gain margin of 1.6, the design value of Kc is dash. So over here, we have been given a block diagram corresponding to the closed loop system. So the first thing that we will do is we will just find the transfer function of this block diagram. And since we have been given this gain margin is equal to 1.6, on the basis of that, we can calculate the amplitude ratio, that is gain margin is equal to 1 upon amplitude ratio. And using this amplitude ratio, we can calculate the design value of Kc. So let's take a look at the solution. .6. So let's take a look on the solution. So here we have been given a gain margin and have been asked to find the value of Kc. So how do we define gain margin? So we define this gain margin as the inverse of the amplitude ratio at the phase crossover frequency. That is, we can write this as gain margin is equal to 1 upon amplitude ratio at omega equal to omega C0, where this is phase crossover frequency. And we define this phase crossover frequency by equating the phase lag, that is phi overall, with minus 80 degree. That is the frequency at which the overall phase lag is minus 180 degree is this crossover frequency. So to find the gain margin, first we have to find this crossover frequency. So we will do that. So the overall phase lag of this transfer function, let's just write the transfer function as G open loop will be GC GF into GP. GC we have been given as Kc, GF, the transfer function of final control element is 10 upon 0.1 s plus 1, and for GP, for process, the transfer function is 1 upon 0.1 s plus 1 whole square. We can simplify this, that is the open loop transfer function as 10 Kc upon 0.1 s plus 1 whole cube. Now, given this open loop transfer function, we have to find the phase lag, that is phi, and equate it to minus 180 degree to find this crossover frequency. So let us write this phi overall is equal to minus 180 degree, and it will be the summation of all this, the phase lag of all these three individual transfer function. That is, you can also write this as minus 180 degrees equal to phi of, let's say, c phi of f plus phi of process. So since this is a constant, the phase lag will be 0, and for this we already write the open loop transfer function as for this entire system. We already found the open loop transfer function as 10 times kc upon 0.1 s plus 1 whole cube. So for this kc we already wrote it as 0, and for this 1 upon this entire thing, 0.1 s plus 1 whole cube, we can write this as, basically it will be 3 times of the phase lag of the first order system with time constant of 0.1. So that will be 3 times of tan inverse omega tau, where tau is 0.1. So let's just replace it, 3 times tan inverse omega into 0.1. So from over here we can write this as minus 60 degrees equal to, this will be tan inverse minus omega tau, so it will become tan inverse minus of 0.1 omega. That is, you can write this as tan 60 is equal to 0.1 omega. So omega, that is a crossover frequency, in this case will be tan 60 root 3, so 10 times of root 3. So this is our crossover frequency. Now we need to find the amplitude ratio at this crossover frequency, and by using this gain margin we can find this value of kc. So that is, we define this gain margin as 1 upon amplitude ratio as omega equal to omega c0, and this gain margin we have been already given as 1.6. So we can write this amplitude ratio is equal to 1 upon 1.6, and now we need to find this amplitude ratio. That is, amplitude ratio is equal to 1 upon 1.6, and for this, again, for this open loop block diagram, for each of these individual block, the amplitude ratio will be the simple multiplication of the amplitude ratio of this individual block. So that will be kc, we can write this as ar1 into ar2 into ar3 is equal to 1 upon 1.6, that is kc into 10 upon under root of 0.1 omega whole square plus 1 into 1 upon the root of 0.1 omega whole square plus 1, and since here we are having this square, so this will be again square. Ultimately this will become 10 kc upon 0.1 omega square plus 1 raised to 3 by 2 is equal to 1 on 1.6. So now this omega value we already have calculated it as 10 root 3. So we can replace it over here. So this will become 10 times Kc upon 0.1. This will be 1 root 3, that is 3, 4. 1 3 by 2 is equal to 1.6. 4 upon 3 by 2 will be 2 raised to 3, that is 8. So Kc will be 8 upon 10 into 1.6. So the final value of the controller gain, we can write it as 0.5. That is 8 upon 16. It will be 1 by 2, that is 0.5. So for the gain margin of 1.6, the design value of Kc is 0.5 is our final answer. So do you have any doubts in this question? Or else we can move on to the last question of today. So in the earlier question, we were given this gain margin and had been asked to find the value of the controller. I think the value of controller gain, that is the design value of controller gain, that is Kc. Now in the next question that we are solving will be related to the phase margin. So this is question number 49 of GATE 2019. And the question is, for a closed loop system shown in the figure, the phase margin is dash. So yes, for this given block diagram, we have to calculate the phase margin. And we define this phase margin as, if you remember, that phase margin is theta plus 180 degree, where theta is calculated at this gain crossover frequency. So let's take a look on the video solution. So we define this phase margin. Let's just call it as PM. So the phase margin is defined as 180 degree plus phi, where phi is the phase lag at gain crossover frequency. And we define this gain crossover frequency that is the omega at which amplitude ratio is 1. So by using these correlations, we will be finding the phase margin of the given question. So let's just write the open loop transfer function of this given block diagram. So over here, the open loop transfer function will be GUL is equal to Kc into e raised to minus of 0.1 s upon 0.5 s plus 1. Now we can write the amplitude ratio of this transfer function, open loop transfer function, as amplitude ratio will be, so for Kc equal to 5, it will be 5. For this exponential or the dead term, e raised to minus 0.1 s, it will be simply 1. And now for this 1 upon 0.5 s plus 1, we can write it as 1 upon under root of omega square tau square plus 1, that is 0.5 omega whole square plus 1. Now we can simplify this as 5 upon under root of 0.25 omega square plus 1. Now for calculating this phase margin, we need to find the gain crossover gain. We need to find this phi at the gain crossover frequency, for which we need to find this omega. And for this gain crossover frequency, the amplitude ratio is 1. So we will be replacing the value of amplitude ratio as 1, finding the value of omega, and then calculating the phase lag to find the phase margin. So let's just put amplitude ratio as 1. So this will become 1 is equal to 5 upon under root of 0.25 omega square plus 1. So this will become 0.25 omega square plus 1 is equal to 25. That is omega square. We can write it as 24 into 4 is equal to 96. That is, we find this gain crossover frequency as under root of 96, that is 9.798. Now we can find the phase lag, that is phi. So it will be equal to, so it will be, so for this it will be simply 0, and for other two terms, that is for e raised to minus of 0.1s, it will be 10 in it will be simply omega tau, and we need to convert it into degree. So this will be minus of 0.1 omega into 180 upon pi, and for 1 upon 0.5s plus 1, it will be tan inverse minus of omega tau. So that is, we can write it as tan inverse minus of tau is 0.5 omega. So from here we can find this phase lag as, let's just replace the value 0.1 into 9.798 into 180 upon pi plus tan inverse 0.5 into 9.798. So this will be equal to minus of 56.13. This tan inverse minus of this entire term will be equal to minus of 78.46. With the phase lag, we will be finding it as minus of 134.60. Now phase margin, we can simply add 180 to it. That is 180 minus of 134.60. So we will be getting the phase margin as 45.40 degrees. So for the given system, we can write the phase margin in degrees as 45 degree, 45.4 degree. I think this much is sufficient for today. In the next question, we will be again looking on this few more examples related to this Bode criterion for closed loop stability, and again related to this phase margin and gain margin. And then we can move on to other control strategies, that is cascade control, ratio control, other such kind of control strategies, and then we can look on the general control problems. So do you have any doubts in any of the questions or the concept related to Bode stability criterion, phase margin, gain margin? If you have any doubt, you can ask, or we can end today's session. So we can end today's session. Thank you for joining.